All right, so in this video, we're just gonna take a dive into more applications. Specifically, I think what we need to look at in this lesson relative to some of the application questions we saw in the last lesson would have been, we're gonna introduce a phase shift here, okay, which challenges the representation of the problem. So one application of periodic motion would be skyscrapers swaying in high wind conditions, right? And they alleviate some of that, we would say, deflection of the building, like from left to right, using dampeners, right? In this case, big, large water tanks in the top of the building, right? So they can decrease the amplitude of the wave by up to 70% or 70% or whatever they tell you. It's going to decrease it by. So skyscrapers sway in wind conditions, high wind conditions. In one case, at t equals 2 seconds, the top floor of a building swayed 30 centimeters to the left, and at t equals 12, the top floor swayed 30 centimeters to the right. Okay, so what I'm going to do is I'm going to use the graph down to my advantage here, just to help me produce what's going on. So I'm just going to label my axes. This is going to be 0, 10, 20, 30, and -10, -20, -30. Okay, and then along here, so this is going to be, I suppose, on my y-axis, I'm going to have the amount of deflection, if you will. And it'd be deflection in centimeters. Okay, and then, so it's telling me, I'm just going to count by twos here along in terms of time. 6, 8, 10, 12, 14. Okay, so there's 24 seconds. It tells me in the question, all right, this is going to be in time, in seconds. Okay, so it tells me in the question that at t equals 2 seconds, the building is at -30 centimeters, like, of deflection. And then at 12 seconds, it says it's at 30 centimeters. Okay, so if I'm just looking at the pattern of what's going on there, right, it looks like in theory, it takes 10 seconds to complete half of a cycle here. And so the other half, right, so from here to here, would be half of the cycle. And so subsequently, from this to, it should take another 10 seconds to get to the low point again. Okay, and so if I were to try and model the situation, I'm just going to connect these points. It'd be a little tricky to do. I don't really know where they're supposed to go, but I do know halfway between here and here, it must have a point in time where there's 0 deflection. So the midway point between 2 and 12 would be 2 plus 12 divided by 2, which would be 14 by 2, which is 7. So that's going to reach, at 7, we're going to reach a point of 0 for this curve. And then the same must be true on the other side. So halfway between 22 and 12, we can do that again if you're stuck on it. It's 22 plus 12 divided by 2, right? That's going to be 34 by 2, which is 17. Okay, so that's the other point in time where that curve is going to be at 0. Okay, so we can get rid of that. So now I can connect these points. Okay. Try to get a nice, oh, I missed it. Okay, so there's a nice sinusoidal representation of what's happening here with the deflection of the building. Okay, now we now know a couple things, right? We know the amplitude. So if in the equation I'm trying to build right here now, this question A is asking me to build something like this. A sine k In this case, it would be t minus the phase shift p, and then plus some sort of vertical translation on the end. That's the equation I'm trying to build. Okay, so that equation has components in it, and components that I can find from the question. Okay, and so what I can find here is the amplitude, A. The amplitude in this question is the distance from the equation of the axis to the max and the min. It has to be the same on both sides. Okay, and so in this case, but there's not a lot to do with this question in terms of the amplitude, because the equation of the axis is actually at 0. Sorry, that was not good. At 0. Right? And so the amplitude is going to be a measurement of high to low relative to that equation of the axis, right? And so I know for this question, the amplitude is going to be 30. Okay, and if I wanted to mathematically prove that, as you've seen in the past, it would be max minus min divided by 2. Okay, and in this question, it's 30 minus negative 30 divided by 2, which is going to be 60 by 2, which is 30. So that's the mathematical reasoning. If you had a question that the equation of the axis was not at 0, okay, the amplitude would have changed. Okay, so we can put that into the equation so far. The other thing we can figure out too is we also know that K, our horizontal stretch or compression, is going to be represented by 360 degrees divided by the period. Okay, and this is the important part of this question. This is kind of, we get to figure out how long does it take to complete one cycle. Well, it looks like it takes 20 seconds to complete one cycle. Right, so from 2 seconds it reaches its low, and then it takes another 20 seconds to reach that same point again at 22, right? At negative, so 22 negative 30 and 2 negative 30. There's 20 seconds in between there. So that's the period, how long it takes. So I would get 360 divided by 20, which would be 18 is my K value. Okay, so there's two components. There's A and K. Now the problem is, and again, just to reiterate what we said at the beginning of this question, the problem is in this question we're going to have a phase shift. Okay, and that's a little bit trickier to manage. So right now this is what we've got, A and K. So what I need to do is I know that one cycle of this curve takes 20 seconds to complete. And so what I'm going to do is I'm going to come down to this graph and I'm going to put on this graph the base graph of sine and cosine, full well knowing that it should be completed from 0 to 20, right? So just a stock sine and cosine curve in relation to the time in seconds. So I know 20 seconds is the period, and so for a stock sine and cosine curve, 20 seconds is going to be 360 degrees. Okay, and if I cut that in half, 10 seconds would be at 180 degrees, 5 seconds would be at 90, and 270 would be at 15. Oops. Okay, so those are your measurements in degrees. And what we can do now, I'll just pretend that the base graphs have an amplitude of 30, no problem there. So what I'm going to do is say, okay, for the sine curve starts at 0. At 90 degrees, it's going to reach its maximum of what would have normally been 1, but this case, because the amplitude's 30, I'm just going to put it at 30. At 180 degrees, the curve's going to come back to 0. And then at 270, it would have been at -1, but in this case with the amplitude at 30, it's going to be at -30. And then it returns back to 360 after 20 seconds. Okay, and so we end up getting a curve that looks like this, our base sine curve. Okay, close, I missed that point. Okay, so now what you can ask yourself is, how could I turn the red graph into the black one. Okay, the red graph, if I'm looking at this, is just y equals sine x. Okay, so how can I turn the red graph into the black one? Well, I could introduce a phase shift or a horizontal translation to the right. How many units? Well, it looks like if I take this point and I shuffle it over to here, I get the red curve. Okay, and so I can represent this with sine using the red curve by saying y is going to equal, the amplitude is 30 sine, the k value is 18, and then relative to time, if I take the red graph and I move it over 7 seconds to the right, so -7, that will give me my black curve that I originally drew. Okay, so that's one option. Okay, remember there is no d value for this question because there hasn't been a vertical translation up and down, because my equation of the axis is at y equals 0. Okay, so is there another way to represent this question though? Well, of course there is. There's lots of ways to represent this question, right? Because these graphs are periodic, right, we could take any of the sine or cosine and represent the black graph using sine or cosine. So what I'm going to do now is, as another option, I'm just going to graph cosine in the exact same way I graphed sine, and then we can figure out how could I turn the cosine curve into the black graph, okay, or the curve, via some sort of horizontal translation or phase shift. Okay, so what I'm going to do here is I'm just going to graph cosine. Cosine would have originally started at the peak or the maximum, and then at 90 degrees it would have been 0. At 180 it would have reached its minimum. At 270 would have been back to 0, and at 360 it would have been back at its max. Okay, and so what I'm going to do, I'm just going to connect those. Okay, so you have to ask yourself now, how do I turn the blue graph of cosine x relative to time into the black graph? Okay, we could actually do this two ways. The first one, again, we can just look at the points and horizontally translate again, right? So you ask yourself again, how can I turn this, or where do I see that repeat itself on the black graph? Well, I see it repeat itself over here. Okay, it's right here. So how do I get this blue portion or blue chunk of the graph over to where it is on the black one? Well, I would take all points on the base cosine curve and horizontally translate them 12 units to the right, right? And so I could rewrite the cosine, I could rewrite this as 30 cosine 18. Those values don't change. What's going to change is the p-value of the horizontal translation, right? So I can move this 12 units to the right. Okay? And I actually have one more option available to me as well. Oops. Okay? It would be if I took that blue cosine curve, vertically reflected it, right? So what I'm saying is this point here, if I'm keeping track of just that point, if I vertically reflect it and put it down here and then move it to the right too, I'd end up with the black curve entirely. So what I could say as well would be y is equal to negative 30 cosine 18 t. Now I need to move this graph 2 units to the right, t minus 2. Okay, so those are the three possibilities, and there's more, I'm sure, too, but three of the possibilities that we could have to represent this situation. Okay, so in part B, the question is asking us if dampers are introduced in the form of large water tanks at the top of the building, that's going to suppress the amount of deflection that happens to the building, right? Or the amount of sway, right? And so they're saying that the dampers decrease the amplitude or how much swing is happening, okay? And it decreases it by 70%, right? And so it does not affect the period or how long it takes to complete one cycle, just how high the curve gets, right? And so it says it decreases it by 70%, which means my new, for part B, the amplitude of the original question is going to decrease by 70%, which makes it 30%, so it'd be 0.3 times the original amplitude of 30. This is going to be the new amplitude, right? And so I'm going to get 9 as my new A value under this condition. So I could rewrite these equations, right, to be y is equal to 9 sine 18t minus 7. I could have y is equal to 9 cosine 18t minus 12, and y is equal to negative 9 cosine 18t minus 2. Okay, so if I were to regraph this as it asks me to in part C, that black graph is now going to go to an amplitude of 9, but the period is going to stay the same, right? And so it still follows the same points, but you can see what happens to the graph this way. Okay, significantly shallower, right? Or doesn't reach the same kind of peaks and valleys. Okay, so there is your final graph. I'll highlight it in orange. Okay, under the conditions of a decreased amplitude by 70%. Okay, so hopefully you find that useful. That's about as hard as it's gonna get, I think, in terms of representing a word problem. In addition to this, we're gonna take a look at actually representing a word problem and then solving for information based on the equation that you've come up with. So that'll be the question below on this lesson. Okay, and then there's an extra package of questions that I'll post as well. Okay.